La la la. All right, I will begin with a word of prayer. So let us begin. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless our work this day, Lord. In your name I pray. Amen. All right, so we are now on to improper integration. So improper integration sort of falls under the category of definite integration in the sense that what we're after might be a number. And so what makes it improper is either the integrand bounds or both do not fit our previous concept of Riemann integration. Right, so to remind you what I'm talking about, integral from a to b of f of x dx. This is what I mean by the Riemann integral, right? The signed area from a to b. Finally. Now, so how do we remedy this? Like, what do you do if the bounds or the integrand don't fit our previous concept? So what do I mean don't fit our previous concept? We could have something like the integral of, let's see here, dx divided by the square root of x from 0 to 1. All right. So what's the trouble here? Why is this improper? Here we have f of x is 1 over the square root of x is not continuous where? Yeah. So this is an improper integral. So how do we make sense of this? What you do is the following. You say, well, I'll define that just to be the limit as a approaches 0 from the right. Wait a minute. Does that make sense? Let's think about that for a second. If we drew a number line, right? And here's 0, and here's 1, right? And you want to do approach 0. What kind of limit is that? Is that a plus or a minus? As we're a would be like here. Do I have it right? Okay. So that is the integral from a to 1 of dx over the square root of x. And then you could do it, right? I mean, this is a, plain old, definite integral. Right? Well, it's not exactly plain. It depends on a parameter a, right? I mean, a is the lower bound here. I put a. But you can do that, right? This is the limit as a goes to 0 from the right of, let's see here, what's this integral? Looks like 2 square root of x evaluated from a to 1. And then how do we calculate that? Limit as a goes to 0 from the right of 2 times the square root of 1 minus 2 times the square root of a. And then how does that limit work out? Yeah, this second piece goes to 0, right? And we're just left with 2. So we say that this improper integral converges to 2. Yep. If a goes to 0 from the right, then the square root of a goes to 0. Yeah. I took the limit as a goes to 0, square root of a. Okay, so look, if I ask this question on the next test, a lot of you could get this right in terms of getting the answer, but still be wrong. How would that happen? What would that look like, to be right but to be wrong? Yeah, you just integrate, pretend like things work out, right? Because to the casual, to the casual observer, it looks like this is just 1 over 2 squared of x. Ooh, excuse me, I can't met. 2 squared of x evaluated from 0 to 1, right? Which would give you, 2 minus 1, which would, 2 minus 0, which of course would be 2. And that answer would be correct, yet the work would be totally nonsense. Yeah. I'm defining converge right now. Converge means that the improper integral works out to a number. But all of the improper integrals that we defined today will be defined in terms of a limiting procedure. So we talk about limits, we talk about converge or diverge, and that terminology extends to here, right? So this is already exposing the general theme here, which is that whatever doesn't make sense in terms of just direct Riemann integration, we have to replace it with an appropriate limiting process. In this case, it was the limit as a goes to 0 from the right. Okay? To give you another example, and this one is more, so I mean, we can't, this is improper notation. Improper thinking, really, because it completely misses the mark that there is a limit that we must think through here. Now, I have not made the case yet that the limit matters, right? You got the right answer, and I don't like limits, so your second way of doing it seems superior, right? Some of you are thinking that, I think. How about this? What if we were to integrate, say, from -1 to 1 of dx over x? Here's the bogus solution. Natural log absolute value of x evaluated from -1 to 1, which is the log of 1 minus the log of the absolute value of -1, also known as 0 minus 0 equals 0, answer 0, yay. Except this is incorrect. In fact, this integral diverges. So in this case, what's the trouble? Y equals 1 over x, right? Has a vertical asymptote right in the middle of this integration region. Okay, so now you could be like, well, the areas cancel, and that's where it starts to get fussy. It depends on what you mean by the improper integral. But let me tell you, what is the convention? What is the standard nomenclature, the standard meaning of the improper integral in mathematics is in fact that this, and I really should use a different color for the other side, have to be considered separately. All right? Like if there's a divergence in the middle of the integration region, then again, these two areas actually are separately plus and minus infinity. And they do not cancel because they're separately divergent. And so here's what the proper breakdown of this integral is as follows. This is integral from -1 to 1, dx over x. That's an improper integral. And when we have a break in the middle, we break it into a sum of two improper integrals. This one and that one. And these get separate limiting processes. So the first one would, let's say, be the limit as b goes to 0 from the left of the integral from -1 to b of dx over x. And then the next one would be the limit, let's say, as a goes to 0 from the right of the integral from a to 1 of dx over x. So these expressions I just wrote down, they're the analytic side of the idea that we approach the area bounded in the hashed blue or hashed red in the limiting sense. We get closer and closer and closer to the vertical asymptote, and whatever that, if that works out to something, we're going to say that that's the integral. If it doesn't, the integral diverges. In this case, it diverges. So let me just do it here. It says limit as b goes to 0 from the left, and what you're looking at there is the natural log of the absolute value of b minus the natural log of the absolute value of -1 plus the limit as a goes to 0 from the right of the natural log the absolute value of 1 minus the natural log the absolute value of a. Oh, my pictures. My two pictures, complete garbage. Curses. How can we fix my picture and save this calculation from its demise? What have I graphed? Grief. This is an otherwise pleasant example. Is this was this 1 over x that I've graphed? -1 over x, is it not? Because it's positive when it's negative, and it's negative when it's positive. I mean, this is -1 over x. So to fix my example, I will just add a minus here, and here, and here, and here, and here, and here, and finally, last but not least, here. I'm sorry, guys. So the first one, natural log of b, works out to -infinity. So this first term, this altogether is like minus a minus infinity. And this last bit here is like minus a, what we got here? Minus a minus infinity. Oh, I have somehow, come on. Oh, it's the old 3 minus problems. I have trouble with 3 minuses. There's a minus, right? But there's also it's the log of a small quantity, which is negative, right? So there's 3 minuses there. So the first term is like a plus infinity kind of divergence. The second one is like a minus infinity kind of divergence, which is correct to the graph. Anyway, they do not cancel. These are separately infinite and negative infinity. So in summary here, the correct conclusion is the integral from -1 to 1 of dx over x does not exist. All right. Now, does not exist means that I can't settle on infinity, I can't settle on minus infinity, it's just neither. All right. Now, if the integral you're working on works out to like a really, if it tends to something that's really growing without bound, then we'll say that the integral diverges to infinity. Some people would say it converges to infinity. It's kind of a philosophical question there. But on the other hand, if the integral in question in the limiting sense becomes very large and negative, well then we'll say it diverges to minus infinity. All right? So either the integral converges or it diverges. When it diverges, it can diverge in different ways, just like we saw with limits before. All right? Example 3. Example 3 is what I say, I mean, these are a little bit subtle, right? I mean, like you could easily miss that example 1 and example 2 were actually improper, right? I mean, if you're not paying attention, it would be easy enough to miss it, wouldn't it? Example 3, if you can't see that example 3 is improper, you're just not even paying any attention at all. So here we go. Integral from 0 to infinity of dx over 1 plus x squared. Like, is this an improper integral? Well, I think the infinity in the upper bound is kind of a clue, right? So what do we mean by this? What is the technical meaning of such an expression? This is by definition the limit. I'll use a t this time. As t goes to infinity, of the integral from 0 to t of dx over 1 plus x squared. All right? This is the definition. In fact, every first step that I've made in these examples so far has been using a definition which I have not written on the board. I will get the projector out here soon and show you the definitions in chapter 11 of my notes, but I thought it would be more meaningful to you if I worked out 3 examples before I did that, so that's what we're doing, okay? So we can do this. This is an ordinary definite integral. What is it? Inverse tangent, right? Of x evaluated from 0 to t. So we got what? Limit as t goes to infinity of inverse tangent of t minus inverse tangent of 0. Somebody tell me what the inverse tangent of 0 is. Tangent of what is 0? Yeah, tangent of 0 is 0, so inverse tangent of 0 is 0. What's the inverse tangent of t? What's the deal with that limit? If you've forgotten, let me remind you. The graph of tangent looks like this, right? To get the graph of inverse tangent, you flip this over the line y equals x, right? The vertical asymptotes become horizontal asymptotes for the inverse function. So these become the horizontal asymptotes of the inverse tangent. And it's something like this. So the limit as t goes to infinity of inverse tangent is, you win some, you lose some, right? Let's see here. So pi over 2. So we say the integral from 0 to infinity of dx over 1 plus x squared, all right, converges to pi over 2. Again, the reason for saying converges versus diverges is because these are all defined in terms of a limiting process. How much credit can you get for an improper integral if you don't write limits in the calculus course? The credit limits to 0. All right, yes. How did I get pi over 2? That's this picture. So the blue is the graph of inverse tangent, right? So as t goes to infinity, we're approaching the pi over 2 asymptote. So, uh-huh. Good question. Yeah. And of course, we could also we could have an example 4 which merges these two concepts, right? You could have something like integral from, say, 0 to infinity of dx over x. This, and then, so here is where it gets fussy. When you have something like this, it's, you basically can just pick wherever you want in the middle. The theorem says it doesn't matter where you split it. I'll split it at 1 because, why not? And so that means the limit as a goes to 0 from the right of the integral from a to 1 of dx over x plus the limit as t goes to infinity, the integral from 1 to t of dx over x. Both of these work out to infinity. All right? They both work out to infinity. Let me draw a graph why that is. This is limit as a goes to 0. Let's think about what that means. This is natural log of 1 minus the natural log of a plus the limit as t goes to infinity of the natural log of t minus the natural log of 1. So these both work out to infinity. This also tends to infinity. So in this case, we'd say that this integral diverges to infinity. All right? Let me draw a picture and explain what's going on here. So the graph y equals 1 over x, I learned my lesson. Y equals 1 over x is where? Like this, right? Okay. And so we're trying to calculate the area under this graph from 0 to infinity. That's what this integral represents, right? And when I break it up, split it at 1, what I'm doing is I'm saying, well, that integral, that area, if it exists, can be split into these two pieces. All right? This one, here's my 1. This area right here, which is this infinity. And then also the tail of it, right, on out to infinity, this piece over here. And what this calculation above shows you is that neither of those are bounded areas. Neither of those are finite. They both diverge to infinity. The picture over here for this one isn't so different looking. What's 1 over, in some sense, it's not so different looking. What's y equals 1 over x squared look like? 1 over 1 plus x squared. It's kind of looks like a bump at the origin. And then it just kind of, like a slow rolling hill, goes back to 0. All right, so what I've done in this example 3 is I've calculated the area, from 0 out to infinity, and we worked it out. It was pi over 2. All right? Now you might wonder, before I'll put the projector up here shortly, but before I get to that, you might wonder, why do we care about these kind of integrals? And the answer is very simply that they come up in all sorts of applications, especially integrals to infinity. These are often useful as sort of a hypothetical extreme for a model or something like that. Or in the study of probability, sometimes you study a continuous variable, right? And so definition, if f of x is greater than or equal to 0, and the integral from minus infinity to infinity of f of x dx is equal to 1, then f of x is a probability density function. That condition that the integral from minus infinity to infinity be 1 is called a normalization condition. Yeah. It converges if the limits in question actually work out to a real number. In other words, if the limits involved converge. It diverges if the limits diverge, in the sense that we've talked about divergence before. Yeah.
So why does the integral from 0 to infinity of dx over 1 plus x squared, why is that convergent to pi over 2, but the integral over the right from 1 to infinity is not, is divergent?
Right, because if you look at them graphically, like it seems like either one is as much as likely as the other to converge, right? They're both functions which as x goes really, really large, they go to 0, right? So apparently the integrand going to 0 is not a sufficient condition to ensure that the area is bounded in such graphs. But the answer to your question is the calculations on the board. I mean, that's why. It's not obvious from intuition that one diverges and one converges. And this is something that calculus has earned us the right to distinguish between these two cases. Intuition doesn't help in this context. I mean, intuition can be misleading. It seems like this might be a finite area, right? It seems like this might be an infinite area, and yet it's not. Now, the probability density function, so the way this works, if you wanted to know what the probability x takes on over, the probability you find whatever it is you're talking about in a certain range of x, all right, what you do is you integrate x times the probability density function. So like, you know, if, just to give you an example here, if we let f of x equal to 1 over 1 plus x squared times what? Times 2 over pi for x greater than or equal to 0. And if we let it just be 0 for x less than 0, then by example 3 and a short calculation, what do we get? So if I multiply this one by 2 over pi, and I define it just to be 0 for x less than 0, this is a case-wise defined function. You guys know about case-wise defined functions? Well, you should learn. I mean, we'll talk more about those. They're defined by cases. But with this definition here, this is a probability density, all right? So maybe x denotes the probability that your ferret is killed by ninjas at time x, right? So there's no ninjas from time minus infinity to 0, and then there's ninjas that come on the scene at time 0 to infinity. So if you wanted to find the probability that your ferret is killed by ninjas over the first 10 minutes, what would you do? You integrate from 0 to 10, I'm telling you, x times f of x dx. And whatever that works out to, that's the... Oh, wait a minute, I'm an idiot. Actually, the probability is just the integral of f of x from 0 to 10. So sorry. So it would be like, you know, inverse tangent of 10 times 2 over pi. That would be the probability that x is between 0 and 10. If I integrate x times the probability density, it's something else. But we'll come back to that some other day. I just wanted to get started on the probability density stuff. I didn't want to finish it today. I have more pictures in the notes I'd like to share with you. So like statistics, all right? Statistics is a major place where we use infinite integrals, all right? One of the major reasons for covering that is that when we cover continuous probability distributions, then infinite integrals occur. All right. Oh, come on, you can do it. All right. Sorry to interrupt this otherwise pleasant lecture. You're like, that's debatable. Let's see here. You probably don't want to attend abstract algebra. Not this semester anyway. They were in calculus too, right? That seems right. Take your time. It's not like we're waiting for you or anything. Yep. I wonder how much of your week is spent doing that. There we go. Apparently 4186 are the magic numbers. Oh, look. 2, 3, 7, 10. This is very exciting. I wonder what this... So it's asymptotically going to what? I don't know. I should figure it's 1, 2, 3, 4, 5. I should stop. All right, let me put this away. So guys, actually, in my notes, I fuss a lot about a separate issue, which is that oftentimes in the treatment of Riemann integrals, we forget to give much airtime to piecewise defined functions. I mean, if you think about it, if the whole theory of Riemann integration is only good for continuous functions, then piecewise, functions has got a jump in it, right? Like this. If I'm integrating from a to b, and my function looks something like this, how do you integrate something like that? What's the answer? You don't? No, the answer is relatively simple. You should approach it if you follow what I'm doing today, you should break it into like limits as you're approaching each jump, right? But that sophistication is actually unnecessary for this case because it always works out like my example 1, like you don't really need the limit. So instead of doing that, we just say you integrate over each piece separately and add them together and say that's the definition for a piecewise defined function. You just integrate on each piece separately and then add them together, all right? That's the definition that you should have been told in Calculus 1. You probably were told that, all right? So, my first definition here is just, I don't know. It's debatable whether or not it matters for you to write this down. I'm more interested, of course, that you actually are able to write down the limits. The first step here, before we worry about how to calculate things, is how we have to worry about how to define things, all right? So in this one, if we have a less than b, if a is not in the domain of f, then this integral is defined to be the limit as t approaches a from the right from a plus to b of f of x dx. This is my example 1 with a being 0. On the other hand, if b is not in the domain, then we define the integral, the improper integral like so, right, in that limiting sense. If both a and b are not in the domain, then we define the limit from a to b of f of x dx as the sum of this piece plus that piece. And there's a theorem that says it doesn't matter which c you pick in the middle, it still works out to the same thing. That kind of makes sense intuitively if you think about what you're doing in terms of just chopping the area in half, right? shouldn't matter where you chop it. If half of it's like divergent, it's not going to matter where you chop it. It's still going to be divergent, right? And on the other hand, if it's convergent, then it shouldn't matter where you chop it. You're still just getting the same convergent things adding together. Not a proof, but that it can be shown that this is in fact independent of C. I'm not going to prove that. We say it's convergent if the limits involved converge. We say it's divergent if any of them diverge. On the other hand, if they diverge in a systematic way so that we can unambiguously say infinity or minus infinity, we'll say diverge to infinity or diverge to minus infinity. Sometimes it doesn't exist in that sense, right? So I think these are examples I actually did. Here's one I didn't do. Integral from 0 to 1 of dx over x minus 1 here. X equals to 1 is where this is misbehaving, right? So I have to say limit as t goes to 1 from the left. You notice that this time I used a t instead of a b. Does it matter? There's only one letter that we shouldn't use there, which is x, right? Or more generally, whatever your integration variable is, you better use a different letter for the limiting bound. Otherwise, you're confusing the point. But anyway, this one works out to minus infinity. Here's another one. 1 over x plus 1 over x minus 1. This one misbehaves at 0. That one misbehaves at 1, so I break it at the halfway point, and I get infinity minus infinity, which is not to say that it's 0, right? We don't cancel infinities like this. This is just an admission that these are separately infinite, and it does not exist, in the same sense of my example 2. This is a picture of what's going on. It's hard to see the green on this silly projector, but you know, that integral I just calculated from 0 to 1, we had a plus infinity from 1/2. I think this is actually the halfway point. I'm not sure about that. It's probably a halfway point by symmetry. It's got to be. And then from 1/2 to 1, we get this minus infinity. They're not connected, so, you know. I will mention there is another concept of infinite integrals called the principal value. In the principal value calculation, it like symmetrically approaches a divergent point in the middle, and it will symmetrically approach infinity and minus infinity. And there are integrals where the principal value exists, and yet the traditional integral that we talk about in here does not exist. So that's something we talk more about in complex analysis. I'll just leave it at that for here, okay? Principal values also have important applications, I think, in optics. But anyway, integral from 0 to 1 of log x dx. All right. Now, I like this example because it brings up an issue, which is L'Hopital's. I wonder, show of hands, who has seen L'Hopital's rule? All right. Good. Every so often we miss it in Calc 1, so happy day. So here we go, integral of log. We know how to integrate log. What was it? So I'm referring to a result. We are I should really, if you've forgotten, you need to work it out again, right? Integral of log x dx u dv. So we get x log x minus the integral of v to u, which is x dx over x. So we get x log x minus x plus a constant, right? Well, so integration by parts gives me this antiderivative, which I evaluated at 1 and then at t, right? Now, as t goes to 0, of course, this piece dies. The log of 1 is 0. So we're left with minus t log t, right? So at this point, we're back to those kinds of fussy limits that we had to deal with back when we talked about L'Hopital's rule, remember? Different indeterminate types. We have to sort through them. We use L'Hopital's rule, algebra, other various forms of tinkering to determine how these indeterminate limits work out. In this case, I brought the 1 over t downstairs to give me log t over minus 1 over t. The reason I did that was as t approaches 0 from the right, the top goes to minus infinity, the bottom goes to minus infinity. So this is type infinity over infinity, which means I can apply L'Hopital's rule, like so, differentiate the top, get 1 over t, differentiate the bottom, get 1 over t squared. And so that simplifies to t, and of course that just limits to 0. And so the answer is -1. So that says that if we look at the log graph, y equals log x, and we look at the area below the x-axis from 1 back to its asymptote, vertical asymptote at 0, that area is actually finite and equal to -1. So here is a text box. What this actually says here is what we mean by, diverging to infinity or minus infinity, all right? As I've already said in class here. And I also say that if we have a set of discontinuities for a function, like if there's a bunch of, discontinuities, then we break up at the discontinuities and integrate from one discontinuity to the next. Like all this is saying here is what I drew the picture of over there. Saying if it's piecewise defined, break it into pieces, add them up. Example 8 here, we kind of already worked today. That's from -2 to 3. I did it from -1 to 1. It's the same example, really. Let's see here. I'm trying to find a different example. Integral of dx over x minus 1 squared. What's the trouble here? This is divergent. It blows up at 1, right? So that means we have to approach 1. And so 0 to 1, 1 to 3, like that. These are separately improper. And that's defined to be limit as t goes to 1 from the left. Over here we had limit as s goes to 1 from the right. I'm using a different letter here and here to emphasize the distinction between these pieces. All right? I mean, yeah, technically you could use the same letter. I'm just using a different letter to emphasize that these are separate limiting processes. So if the one works out to infinity, the other works out to minus infinity, that does not entitle you to cancel them. Far from it. So anyway, but even so, this one works out to infinity plus infinity anyway, so nobody here would cancel and give 0 anyway, right? I mean, this one is diverging to infinity. Oh, this one's horrible. Look at this. -2, 2, and 0, all points where the integrand's not defined. But as we look at this integral, we only face what? 0 and 2 are actually in the domain of consideration for the integration, right? So that means I have to approach 0 from the right to take care of that improper point. And I have to approach 2 from the left on one side and from the right on the other and add these 3 improper integrals together in order to calculate this integral. I think they all separately diverge. And I had the good sense to not actually write out the details. Here's another one. Integral from 1 to 2 of secant x dx. What's secant x? 1 over cosine. Where's cosine 0? Pi over 2, otherwise known as 1.57 blah, 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 blah. That's between 1 and 2, right? So pi over 2 is a divergence. It's a place where secant blows up. So that means I have to approach pi over 2, and I have to split this integral into these 2 improper integrals and calculate each one of these separately. So we need a separate limiting process for each one of these to sort through this integral. Here's a picture of what's going on. Secant looks like this. We're asking what's the area between this and that, right? So you're going to get these 2 separate. What do you think? Does this diverge or converge? I'm pretty sure it diverges because the integral is secant plus tangent. And if you look at those limits, you're going to get like log of infinity when you work it out. So I believe these both separately diverge. Let's see if I have another good example to show you. Let's see here. Have you ever thought about x over the absolute value of x? What is this function? let's think about this. This is a case-wise defined function, right? So if x is less than 0, we have x over minus x, right? If we have x greater than 0, then the absolute value of x is just x. So we have x over x, right? In other words, this is simply minus 1 for x less than 0, and it's 1 if x is greater than 0. So this function has a discontinuity at 0, right? I wonder if you've ever seen this. We could write f of x equals x over the square root of x squared. That's a formula for the same function. Like Marvel needs more advertising. Let's see here. Okay, so, fun thing. What if you differentiate this? So we have what? Dx dx times the square root of x squared, right? Minus x times d dx of the square root of x squared, yeah? Divided by the square root of x squared squared. How's that work out? So we have, what we got here? Square root of x squared minus, how's that work out? X times 1 over 2 square root of x squared times 2x, yeah? Which is what? So I guess I'll multiply by square root of x squared over the square root of x squared. What have I done? Oh, man. Yeah, well, anyway, apparently this works out to minus 1 or 1. Wait a minute. What does this work out to? Yeah, it should work out to 0. Did you guys see it? It does? Well, it's not obvious, but okay, listen. So we got like 2 more days to talk about improper integrals. I just wanted to get us started today, and I'll try to look at harder examples in the days to come, okay? Sorry I don't have your test graded yet. I have not even looked at them. Whatever you did, I don't know about it. You could be the best, you could be the worst. I have no idea.